way. And so thank you for all the kind words and things that you've been sharing with us and what your experience has been like with us in your home. So again, thank you so much for sharing that. It really is like a ray of light in my in my very intense world right now. So so thank you so much. Okay, so for today, we are going to get started. Give me just a second. I'm going to get my slides up. If you've never participated in a class with us, I want to extend a special welcome to you. Usually our sound works first thing out of the as soon as we start, but I apologize for the sound problems this morning. Okay, so if this is your first time with us, my name is Aurora. I'm a mechanical engineer, university instructor. I fly airplanes since I was 17, and I started teaching college when I was 21. So I totally love math and science, and I love bringing it into your home with your kids. So I am really excited that we'll be sharing this with you. Today's topic is especially important because we're going to be talking about civil engineering. And I actually taught civil engineering and civil engineering type classes, statics, dynamics, you name it, vibrations, laboratories at the university. And so some of the things I'm going to be showing you actually came from those lessons. Actually, I got my start when I was a PhD student at Stanford University. I went around with my pickup truck. Any parents ever drive a pickup truck? You know, the ones with the clutch you had to slam all the way to the floor before it would even remotely engage. That was mine. And so I would drive my Ford F-150 around. So I would teach the university classes, and then I would also teach K through 12 classes throughout the county. And I would bring all of my equipment, and it was by contract. I would call teachers up and say, hey, do you want a Cal Poly instructor to teach science in your classroom? And they said, yes. So year after year after year, I would do that. And I did that for a number of years. And then my brilliant husband got the idea, like, wow, why don't we film what you're doing? And so people have been asking, what curriculum are you using? Like, who developed it? And the answer is, well, I did. And I did it based on all those years teaching mechanical engineering at the university, in addition to taking those lessons and bringing them to the classroom. So that's where this curriculum's coming from. And honestly, it's for any age. So if you've got a 5-year-old that's on fire, excited to build robots, and you've got a 10th grader who wants to learn everything about astronomy, one of the questions is, what grade level are you from? And what little package does my kid need to be in order to do it? The answer is, try it. If you like us, stick with it. If it's not your thing, that's no problem. Move on to something else that does. So we've had a lot of people ask, well, what age level? You know, is this for 6th graders? Is this for 6-year-olds? And the answer is, it's for anybody who's interested and excited to learn real hands-on science. And so there is no age requirement. In fact, we even have teachers that have said, hey, I'm actually not a student. Is it okay if I watch your stuff? The answer is absolutely. So we're for anyone interested and excited, and there's no restrictions. If you want to learn about science, then let's do it right now. Does that sound good? Okay, so here we go. Technical hiccups are all solved and set aside. We are going to be learning the art of civil engineering and the science of it. And by the end of today, it's going to be about 20 minutes long, 25 minutes. At the end of today, I'm going to be issuing a challenge. And so stick with me, and I will show you exactly how to do civil engineering. And by the end, you will have solved 3 major engineering problems that are actually real. These actually happened. Okay, so let's take a look at what it is we're going to be learning. So if we're going to talk about engineering, specifically civil engineering, what do you think it is? So tell me out loud, just pretend I can hear you, pretend we're talking, and you can hear me now, thankfully, and I can hear you. Tell me, I'll be quiet for 10 seconds. What do you think engineering is? And if you already know, tell me more, like, well, what specifically is civil engineering? What do you think? Just take a wild guess. Ready, set, go. Okay, you think you got it? All right, so a civil engineer, what does it say on the slide? Read it to me. What does it say? Right, okay, so according to the U.S. Bureau of Labor Statistics, civil engineers design, construct, supervise, operate, and maintain large construction projects and systems. What is that? Basically, a civil engineer will design and build things like bridges, dams, roads, buildings, airports, tunnels, and systems when you flush the toilet. So it's one of the oldest branches of engineering, and when people first started living in permanent settlements like cities and towns, they started to shape their environment using the rocks and the trees that were around them to be more of what they wanted and what they needed. And so early engineers built things like walls, roads, and bridges. They also did things like dig wells for water and made irrigation ditches and trenches. And the settlements grew into larger towns and larger cities. And people, as more people came along, they needed more clean water. So then civil engineers also started doing things like water filtration, getting rid of waste, and also cleaning up the streets and roads that everybody's been using, right? So that's where a civil engineer comes in. Okay, so there's a difference though. If you've heard people talk about architecture, civil engineers and architects are a little bit different. Architects are the ones that will focus on the aesthetic principles of design. So they take more art-related classes, fewer engineering, fewer science classes. Civil engineer will focus more on the science and the engineering side of things. So you'll take fewer art classes as a civil engineer, and you'll learn more physics than you would normally do if you were just a regular architecture student. Civil engineers are usually labeled as more difficult than architecture, but architecture is also a difficult engineering in terms of, it's intense. There's a lot that you have to study. So civil engineers will build things that architect students necessarily won't, like hydroelectric dams, canals, roadways, other structures that are more functional for the community. So that's the main difference between the two, but there is a lot of overlap as well. Okay, so civil engineers aren't just building things. They also research and test how well different materials can withstand things like earthquakes, right? There are 50 earthquakes every day in the worldwide. And they're working on bridges that can detect problems and send emergency alert warnings when they're in danger of collapsing. They also work with artists to help preserve historic art structures. This is the Wyatt Towers Museum in Los Angeles. So most civil engineers are either stuck in an office or behind a computer or in a lab doing experiments, which may or may not be stuck, depending on what your definition of unpleasant is. A lot of things can be really cool, doing simulations in computers, designing things, doing a lab, doing experiments. Civil engineers, though, get to do both, and they also get to go outside at the construction site where they can make sure their work is done right and solve issues that come up. Now, I actually put together a quick little collection of my favorite construction issues that actually happened. Can you see if you can solve the problem that happened with each one? What's wrong with each picture? Go ahead, point it out. Tell me out loud. What's wrong with each picture? Did you notice anything unusual? Yeah. Did you see the chimney inside the house? Right. And how wheelchair accessible does this look? Yeah, and I don't know how you'd get from here to there. Okay, good. What about these? I mean, how would you park your car when your garage is on the second story? Okay, so you understand why it's important to stay on top of things. That's why civil engineers need to be at the construction site. I mean, everybody makes mistakes. We're all human that way. It's totally natural. Now, if you've ever teetered on the edge of a diving board, you know that the board's going to flex under your weight, right? The heavier you are, the more it bends. So at the top, now one I want you to notice, because we're about to dive into some civil engineering challenges, is if this was a diving board, the top of it gets slightly longer and the bottom of it will get slightly squished. Okay, the underside will get slightly shorter or compressed. So the top of the board experiences pull, which is tension, lengthening it, and the bottom is undergoing compression. Now, you've ever done this with a pencil? You'll take like a pencil in your hand, and you can do this now if you want, and just grab an old pencil because you're going to break it. You're going to kind of feel where it flexes and even start to hear the crack. Now, as you apply more and more pressure, that top is under tension, the bottom is under compression, and when it breaks, I got a picture of it here, you can actually see that coming apart. So when you bend the pretzel, when you bend the pencil, it has no problem going back to its original shape because wood is pretty elastic, and that means it can bend quite a bit before it breaks. This comes in handy if you're a tree, right? When the wind comes blowing by, that allows you not to break in half every time there's the slightest gust of wind. Now, when you actually bend the pencil enough so that it breaks, do you see it now? So look at it here and notice what happened. And notice how it broke differently on the side under tension versus the side where your thumbs are under compression. So as those molecules get pulled apart, they break in a certain way. And if you don't bend too far and you just relax it, it'll, it won't break in two, right? So objects that have an elastic limit, how do I want to say this? Objects have an elastic limit. And when you go beyond that elastic limit, that's when the molecules can't hold together anymore. And that's when stuff starts to break. So if you've ever done that with a rubber band, you stretch it, goes back, stretch it, goes back. And if you stretch it really far or enough times, enough cycles, you can actually get that rubber band weakened. Or if you put the rubber band in the freezer and then you try to do it and you pull once and the whole thing breaks, and you're like, wait, what happened to my rubber band? It's because you changed the temperature, you changed the environment. That's why sometimes the seals in your car don't work as well in really cold environments. Things tend to get brittle and break apart. Okay, so keep these ideas about tension and compression in mind. Are you ready for your skyscraper challenge? Here we go. Let's take a look at some, well, actually, let me talk about what a skyscraper is first. Let me show you really quick. A skyscraper, this one is the skyscraper in Dubai, and it was completed in 2009. It is the world's tallest skyscraper, and it's nearly a half a mile high. So this thing has 164 floors, 900 apartments, 304 hotel rooms, and 58 elevators that go about 22 miles an hour. So when we first started building these things, early skyscrapers were really dark, and they were small because the walls were thick and because they were made of heavy stone. When iron and steel started to replace the stone in skyscrapers, as we learned more and more about how to build these things, the buildings were about 10 stories high, but the rooms were still pretty small, and they didn't have a lot of windows because windows at that time weren't structurally sound. So the first elevators were invented to help people get in buildings that were higher than 4 to 5 flights of stairs. So originally you wouldn't have skyscrapers that were very tall. They were usually limited by how far people were willing to walk. And so as elevators were invented and we stuck those things inside the buildings, now the buildings could get even taller. Okay, so what do you think one of the biggest concerns with a skyscraper like this is? With any skyscraper, really. What do you think one of the biggest concerns is? Take a wild guess. Tell me out loud. I'll give you a hint. Yeah, wind. Wind is a big issue with skyscrapers. Tall buildings that are like 1,500 feet usually have to be 50 times stronger than 200-foot buildings. So that's a lot stronger, not just a little stronger, but a lot stronger. Okay, so imagine that you are a real civil engineer right now. And you are walking into your civil engineering office one morning and you find out on your desk you've got 3 skyscraper emergencies right now to sort out. And you didn't even have your coffee yet. So here's the first one. And by the way, these are real. So in Chicago, Illinois, a very old 5-story wood apartment building burned to the ground months and months ago. And since then, it's already been decided to rebuild it into a 50-story apartment building, 50-story. You, the civil engineer, need to tell the construction crew that the type of material the new one should be made out of. Okay, that's going to be your recommendation. This new building is a lot taller than the old one, right? 5 stories versus 50 stories. So it's going to be heavy. So the lower levels experience a lot of tension or compression. Which one? That's right, they're going to get squashed, so it's going to be compression. The weight of the tower is going to squash those lower levels, right? So what do you think? What should we build our skyscraper out of? Should we use stone, steel? What do you think? Okay, well, let's start to take a look at some of these materials that you may or may not have experience with. Okay, so what do you think about stone? Stone is heavy in compression, right? And like sidewalks are made out of stone. It's stone, and for things like trucks and stuff, it's strong. It's very, very strong in compression. It can take the squish factor pretty easy. It's pretty inexpensive and it won't burn in a fire. But what's the problem with stone? Have you ever tried to move a big rock? It's really heavy. And if you make an entire 50-story building out of stone, what's going to happen? It's going to sink right into the earth. Okay, so just stone is kind of out. Let's take a look at our other options. What about steel? Steel can be stretched, squeezed, twisted, move around without breaking, right? It's good and it's really good in tension. It's a good choice for tall buildings. The Sears Tower in Chicago, see the buildings with the 2 antenna looking things on the top? It's made entirely out of steel. It's not a bad choice. Steel is good at normal temperatures, but what happens with steel, what's the problem? It melts at about 700 degrees. So if you're worried about a fire, this is not a good choice. And your boss just said, hey, make sure this new building is fireproof. So how would you fireproof steel to slow heating up of those steel structure beams inside? What about concrete? Actually, steel reinforced concrete, you see a picture of it there on the lower left. This is the best option here out of the three because steel is super strong in tension. You can pull and pull and pull and it doesn't break easy. Concrete is strong in compression. You can squish and squeeze without a problem. So together, you can squish and squeeze and stretch this building without breaking it. Phew, you just did it. Challenge number 1, out of the way. So you can go to that construction company right now and tell them, what are you going to make your building out of? That's right, steel reinforced concrete. Okay, whew, we did the first challenge. You ready for the second one? Okay. Now these, as I mentioned before, if you've just joined us, my name's Aurora with Supercharged Science. We are doing a class in civil engineering. The little link here on the bottom, I forgot to mention, if you want to sign up for more classes, there's more free classes here. So just sign up at superchargedscience.com/class. You can do that anytime. Okay, so we did challenge number 1. Let's take a look at challenge number 2. Now again, these are real challenges. Okay, in New York, a 300-foot tall building that is currently still being built is starting to sink because the soil is too soft on one side and it's really rock hard on the other. And your boss is worried it might end up looking like the Leaning Tower of Pisa. You see that there on the, on the right? So what do you do? He wants to know, is it worth continuing to build it? What do you do? Okay, so let's take a look at your options. Okay, so option number 1 is pretty obvious. Stop building, right? Okay, or you also have another idea. You could use a chemical glue, mix it up to firm and harden up the soil, or you could dig deeper to strengthen the foundation. Which one do you think we should do? Stop building, or inject glue to harden the soil, or dig deeper? Which one do you think? Okay. So if you stop building, that seems like the logical first step, right? You have to stop building in order to do the other two. But if you stop building just means stop construction entirely and scrap the whole project. Okay, so if you do that, you've already spent a lot of money on the project already, and now you're gonna have to spend even more cleaning up the project, and you'd still have to build it somewhere else, which is now totally out of your budget for the whole project. You don't have enough money to stop, clean up, and start over again. Okay, so scratch off number 1. What about the glue mix-in? Yeah, you could use glue, but it's really, really expensive. Forgot to tell you that, oops. Almost as much as the entire building itself, and it doesn't, so you don't have enough money for this one either. Yeah, that happens a lot with projects, in case you were wondering. Running out of money, running out of cash is a big problem. Okay, so let's take a look at the third one, digging. Okay, well, engineers, when they have to build on things like sandy or soft ground, they'll often go on and dig even further than they normally would to find the kind of soil that can support huge amounts of weight like a skyscraper is, because the footprint is so small. It's like you ever seen like a high heel shoe, like a lady's high heel shoe, right? So you've got all their weight on this teeny little, maybe, 2 millimeters across, right? And all their weight is on that one area. It's a lot of pressure that gets pushed on there, right? Their weight doesn't change, but the amount of area, if they rock back on those heels have to be really strong. It's kind of like what a skyscraper is doing. Okay, so the ground beneath a 1,500-foot tall John Hancock Center in Chicago, that's the tall building with the big X's going up it here. This one was dug and dug and dug until the engineers hit bedrock nearly 200 feet below the surface. So they had to dig for quite a bit. So what do you think we should do? Stop building's too expensive. Injecting chemical glue is too expensive. Digging and digging and digging, that's not going to eat up your budget nearly as much as the first two. All right, so go tell your boss it's time to start digging. So go get the machines you're going to need to strengthen the foundation below before any more work is done. How does that feel? Does that sound good? Okay, so how are you guys enjoying these so far? Do you want the last challenge? Okay, here we go. Challenge number 3. Now, by the way, my name is Aurora, Supercharged Science. We're doing civil engineering. These are real engineering challenges that have happened, and we are learning a bit about the materials along the way, as well as how engineers kind of troubleshoot things. Okay, here we go. Third one, San Francisco, California. In San Francisco, a 75-story steel reinforced concrete skyscraper. Did you get all that? Okay. So a 75-story steel reinforced concrete, like the stuff we saw in the first challenge, is about to collapse because it was designed wrong. Inside are hundreds of apartments, shops, and a movie theater, and the owners want to open up a lot of space and have huge windows on every floor. How are we going to do that? Okay, first you could put columns all the way up and down the entire building, right? Or you could put a core of steel beams up the center of the building, right? Or you can encase the whole building in a cage, kind of like putting a network of steel beams and bars around it. We've got 1, 2, and 3. So what do you think? And this is not the building. I'll tell you about this building in just a minute. Okay, so what do you think we should do? A 75-story steel reinforced concrete skyscraper is about to collapse because of a poor design. But now the owners want a huge windows everywhere, and they also want a movie theater. So what do you think we should do? Should we put a huge network all the way up and down? Should we just put a core, or should we put a cage around it? What do you think? Okay, if you do option number 1, what's the problem? Okay, it's going to be really dark inside, just like skyscrapers were when we first started building them. And it won't have a lot of space because there's going to be like pillars everywhere. Have you seen these? Have you been in buildings like this where everywhere you look, there's like a beam, like pillar. You can't actually, it's great for playing like tag if you're a kid, but it's terrible if you want to be able to see your kids and find out where they all are, right? Or especially in a movie theater. Can you imagine what that would look like? And it's also really expensive to put that many beams inside of a building. Yeah, and imagine what the movie theater would look like, right? You probably couldn't see the screen very well. Okay, so option 1 is out. Well, let's take a look at option 3. What about a cage on the outside? Like a steel cage? Yeah, it's inexpensive. It's effective. What do the owners want, though? Are they going to like that? No, because what did they want? They wanted a lot of big, open, airy windows. Hello, architect majors, right? Okay. They wanted a lot of big, open, huge windows. And you're now going to cover them up with an extensive, not expensive, framework, like a shell or a cage around the building. They're probably not going to go for that one either. Option 2, let's take a look at that one more time. It has a central core running up and down the building that will form like a rigid backbone with plenty of space for the windows, apartments, movie theaters, and it also gives extra support in high winds. Remember we talked about that's a problem for skyscrapers. And as an added bonus, what could you do inside this core? Have you spotted it yet? How do you get up to the top floor? Could you put an elevator in that space? Absolutely. The Chrysler building here in New York has the number 2 option. It has an inner core, and this is the building you see here on the right. Okay, so you can go tell the owners, no problem. We are going to put a core of beams and ask them, how many elevators do you want to stick in there? Give them some options. So how was that? Does that make sense? All right. So we've done a lot of engineering. Oh, you know what? I do have a bonus. Do you want like one more? Okay, hang on. Wait, I didn't finish this one. Hang on. You can't put a core in there. Why? Because what is San Francisco known for? Earthquakes. That's right. Okay, so you could put a core in there, but it's going to take some extra analysis. This is a little bonus content on there, right? There was a reason we chose San Francisco. How do you reinforce a building in addition to the inner core that we just talked about so it doesn't break when it shakes back and forth? Okay, so you've already huddled up with your team of engineers that talked about it, and they've come up with 3 more ideas for you. You ready? They said, well, we can have crisscross diagonal braces up the center core like a power line tower here. Crisscross, and the elevator would go inside, and that whole thing would be inside of the building. Okay. Or you can add long supporting arms and kind of prop things up like this, right? You ever seen this when like a wall is about to fall over? The first thing people do is they put these arms that are now in compression or tension. Which one? Yeah, they're in compression, right? They're being squished because they're pushing the wall back up. Or another idea is to put a large solid concrete blocks up the shaft to make it more like a rigid backbone. Okay, so lots of big concrete blocks stacked on top of each other inside the core inside, kind of like this. Okay, so which one do you think is best to withstand earthquakes? Okay, so the power tower thing, number 1, you liking that one? This idea is okay, but steel is kind of expensive and it's not going to add much rigidity for the money as another option after you do your analysis. There's another option that's actually better. It's actually less expensive and gives you more rigidity. The long arms, what do you think about this? Nah, they don't hold up well, because why? Well, if there's an earthquake, is this ground shaking also? Yes, it is. Sometimes it'll shake in the opposite direction than the building is shaking, and so it winds up pulling the building down instead of supporting it. So option 2 is just not good. How about option number 3? A concrete backbone. Yeah, that's actually the best idea. So the solid concrete walls, we call them shear walls, S-H-E-A-R, shear walls. They have a lot of stiffness, which means that when the ground shakes, the shear walls keep the building solid and strong because they are stiff in the horizontal back and forth motion. Now, the first Interstate World Trade Center in Los Angeles, California has a solid core running up and down the center of the building. So this one can withstand an earthquake up to 8.3. Isn't that cool? All right, so now go back to your boss and say, hang on, I have an update for you. We're going to be using concrete shear walls up the center core. That's right, up and around. Okay, so yay, you did a great job. You solved 3 civil engineering problems that really happened, and I showed you examples of where the solutions actually existed today in today's world. Now, you ready to build your own challenge? If you are, say, oh yeah. Okay, so you figured out 3 different skyscraper challenges, right? You're starting to kind of get the feel of what it's like to be a civil engineer. It's not all just designing things. You have to solve problems too as they come up, and not just duct tape things together, but really be clever and understand what's going on. So how about we build something for real? You ready for this? Okay, so if you don't have any materials, don't worry. I have a super simple, easy engineering challenge for you to do right now. And this challenge is actually going to be open for the next 2 days. So here's what you want to do. Here's what I want you to do. If you're up for the challenge, I want you to get a sheet of paper, a piece of tape, and a heavy book. Wait, don't get it yet. Just hang on, just listen. Supercharged Science is issuing an engineering challenge. Now, you will have the next 2 days to design to figure out how to use a sheet of paper to support a book at least an inch off the table. The only materials you're allowed to have is a sheet of paper. You can have more than 1 sheet if you'd like, but don't make it like a whole ream. We're just talking like just a couple of sheets. More than 1 is fine, okay? And only tape. And you can have as many books as you want, okay? Now, you can also go for challenge number 2. You can do either one or 2, or you could do both. The second one is, I want you to support an egg. If you don't have an egg, use a baseball or something. At least, how high? 18 inches up in the air using only newspaper and tape. Okay, and we're asking you to use 1 newspaper or less, not 1 sheet, but 1, entire, like the newspaper that would show up in your mailbox, that kind of newspaper, okay? All right, now, do you expect to do this challenge and have it work perfectly the first time? Absolutely not. What did we just talk about? All these people that thought they did a great job, and this was after they did all their testing, and then built skyscrapers and still had problems. So if you're asking, oh, I don't know if this is going to work, my best advice, try it. See if it works. Try it. See if it works. Engineering isn't about getting the perfect answer every single time, which is unfortunately how a lot of curriculums teach us, especially when it comes to math and science. They'll spit out some fact, you have to spit it back, and then you get the right answer, and now you can move on to chapter 2. That's not what science is, and engineering specifically is about. It's about seeing a challenge, seeing a problem, figuring out a solution, and troubleshooting and iterating your way to actually figuring it out and doing it on your own. For example, this is not a real picture, but sometimes I've seen this one on the internet. Problems happen, and it's okay. Just because somebody is an engineer doesn't mean that they don't make mistakes. Everybody makes mistakes. The problem with making a mistake when you're a civil engineer, though, is that everybody knows about it, right? Because it's a bridge that's not right, or a roadway that's not right, right? Now, sometimes engineers have to fix other people's mistakes, as you saw, as we talked about earlier in the class. So a lot of engineers actually like it when they mess up. They like it when they make a mistake because they get to learn something they didn't realize before. And that's actually true for myself as well. When I get it right, it's not nearly as interesting. It's like, oh, that feels good. Now I'm on to something else. But when I really make a mistake and I'm like, whoa, I had no idea that was going to catch on fire. What happened? I get so excited because I get to learn something. So if you've been a little hesitant, or parents, if you've, don't do this, don't do that. Allow your kids in a safe manner, of course, we're talking about common sense here. Allow your kids to make mistakes, roll around with it, and just that, because the fear of making mistakes is often what stops kids from innovating in the first place. We want you to make mistakes. We want you to mess up, because that's where some of the best ideas come from. If you've ever heard of like ScotchGuard or the 3M Post-it notes, you can even look up the 100 best engineering mistakes or scientific mistakes that now we use in everyday life. And so we want you to try to build a building. And yes, it's going to mess up the first 100 times you do it. Well, maybe it won't take you that long. But don't expect it to be perfect the first time, because it's not supposed to. Your job is to learn something, and you learn something when you notice something that maybe you hadn't noticed before. And so that's really what we're after. Science, again, isn't about what you know. It's about how you handle new stuff and about how you handle what you don't know. So when things don't go right, instead of getting frustrated, well, if you get frustrated, go out, have an ice cream, go take a walk around the block, whatever you need to do just to relax, and then come back and say, all right, what's really going on here? and then you can hit it again. Okay, so I'm going to wrap this up. I'm going to issue the formal challenge. So you can either do the sheet of paper challenge, and you can see kids have done it here. You can also do the newspaper tower challenge. And the Supercharged Science is officially issuing an engineering challenge to win prizes. So all you have to do, kids, is send a video or photo of your entry by the 16th. That's in 2 days. You can either do it to our Facebook page, facebook.com/superchargedsci. You can do it to our website. My email is aurora@superchargedscience.com. And you can put your submission in that way as well. We have prizes for anyone that is able to meet the challenge. Here, let me show you the challenge. So anyone that can do these challenges, so this is a bar, and if you can jump over it, then you will win a prize. We are not just giving away one prize, we are giving away lots of prizes. And I totally am excited to do it. And if you do challenge number 1 and challenge number 2, I actually have 2 different prizes for you. So we're going to wrap stuff up so you can get started building. Remember, we talked about, for the newspaper one, I do have to clarify 2 specific things. Challenge number 1 is you're supporting a book an inch off the table. Number 2, with the newspaper challenge, there are 2 other things we're going to be looking at. You have to expose your newspaper structure to either a fan or a hairdryer for 10 seconds. Because remember, we talked about wind. So if your structure is able to withstand wind, then that's the ones that we want to see. So it's not enough just to build a tall tower. If the first sign of, if I can blow it over, it's not going to count. So you have to show me it's standing in a stream of wind. It doesn't have to be wind on full blast. We're just talking about a moderate breeze. And the second thing is, if you have an option, if you've built a number of them and they work, pick the lightest one. So the one that has the least resources, because honestly, engineers usually have a limit on what exactly they are allowed, like what their budget is and what materials are available to them. So if you have a couple of options, let us know which one is the lightest and tell us, how many newspapers you used, for example. Okay, let me put the challenge back up. So go ahead and take a screenshot of this. We're going to post this on our website as well. If you know anyone else that would like to participate, please do invite them. We would love to see a photo or video of your entry, and also to give you a prize as well. So make sure you enter in your prizes to aurora@superchargedscience.com, or you can submit it through Facebook, facebook.com/superchargedsci. I know Facebook's been giving some people problems with submitting links and pictures and stuff, so you can just use regular old email. That'll work. But again, so thank you so much for joining me with our class today. I'm going to see if we had any good questions. We want to. Can you imagine Aurora's long hair with one of those? Probably. One of what? I wasn't part of this conversation. Okay, can you use regular paper with challenge number 2? Yes, you may use regular paper. You're going to need more than one. Is a big metal ball behind her one of those things? Oh, is that the... Yes, I look like a giant hedgehog porcupine. Absolutely. Okay, how do you send in your experiment? Shannon, all you do is you send me, use my email, aurora@superchargedscience.com, and send me either a short little video, or you can send me your photo of doing it. We don't publish them without your permission. So if we like one, we're like, oh, I want to show everybody that one. We'll let you know, but we just want to see your entries. Okay, other questions. You changed your answer after the answers were displayed. I'm not sure about what that was. Okay. I think the column still could work. Oh, okay, great. Other questions. Hollow tube designs. Let's see. Other questions? Can we do the challenge, both challenges? Yes, absolutely. Do both challenges. Let as many people know about this so they can do it too. We would love to, even if people have no experience with Supercharged Science, let them know. Just take a screenshot here. Just take a screenshot of this and pass it on to them, and they can totally participate. You don't need to buy anything. This isn't anything there are no strings attached. We are doing an engineering challenge, and we want to see what you as kids can learn. I'm going to tell you a quick little story. I actually got my start in engineering through NASA by one of these challenges, and that's why we're doing it, because NASA issued a robot challenge way back when they were like 25, 30 years ago, when they were doing the Mars rover. They opened it up to all schools in the area to design robots, and I was one that said, hey, I want to do that. So and what they were looking for were new ideas, innovations and creative ideas from kids that maybe their scientists hadn't thought of. So they held this big open forum. Thousands of kids participated, but they had an engineering challenge. It was one of the first ones that was done on that scale at that time. They still have robotics engineering challenges as well. There's a lot of civil engineering challenges. If you haven't heard of the concrete canoe or design a city challenge, those are other ones as well you can get involved with. But this is the Supercharged Science one as well. What are the prizes? That is a good question. I am going to be giving you well, it depends on which challenge. So we have a number of different challenges. We have a couple of different, whoops, hang on. Let me see if I can find it. Where did it go? I actually have it printed out. The prizes depend on the level of the project that you let us know. So we have 3 different levels of prizes. So we have one for effort, like, hey, we tried it, it was a disaster. I'm like, hey, here's a great prize for you. And we also have a prize for someone who is the most creative and the most amazing. They have a different prize. And the third prize is for ones that actually succeed in doing the challenges, and they have their book at least an inch off the table. They've got 10 books, in fact, or whatever, or they've got their egg at least 18 inches, and then we have another prize. So we have a couple of different that we are going to pick and give to your team, and it's just our gift to you. Okay, so I'm doing the book. Okay, what does CPSS mean? Cal Poly Space Systems. So when I was a graduate student, when I was a professor, I had a graduate student that was so into rockets, and so he later took our ideas and formed Cal Poly Space Systems, and as a thank you, their club gives me their old rockets that they don't use. So this was a rocket that was made by, oh, you can't actually tell it's a rocket. This was a rocket that was made by, here, see? Here's the nose cone, it comes off, and here's the fins. It's kind of big. This one I think only went up like 4,000 or 5,000 feet. And so these are rockets that are made by students in the rocketry club at Cal Poly. And so this is the only one that fit in my office. The other ones are kind of big. Other questions? Can you use more than one newspaper? Yes, but we don't want you using more than one stack. Like, you know how the newspaper comes to your house? Just that bundle. We don't want you using like 10,000 pieces of newspaper. So just like one news, like when you would buy a newspaper for, it used to be a quarter, whatever it is now. When you would buy a newspaper and you get like a stack of pages, that's what we're looking for. Okay, so let's go ahead. 1 sheet of paper is allowed for the first challenge. If you need more, I would say less than 10 for the first one would be fine. So if you need more than 1, that's totally fine. Okay, so thank you so much, everyone. I am so excited that you will be part of this challenge. How many agree that Laura deserves past 30? Thank you so much. Actually, the 2 most popular questions I get is, what do I have for breakfast? And what kind of makeup do I use? So I have rocket fuel for breakfast. I don't use a whole lot of makeup. So I think part of the secret is being surrounded by kids and just doing what you're passionate about. So, and thank you. You guys are my new best friends. Okay, so yes, only 4,000 to 5,000 feet. Okay, so let's go. If you have other questions, let me know. Aurora@superchargedscience.com, and you can email me your questions if you want to know particulars. Let me put this up again so you can take a screenshot of it. Go ahead and do that right now. And we will be posting this later today, and as well as posting this video so you can have other people watch it that you think might be interested as well. All right, everyone, go ahead and take care and have a wonderful week with your kids. I will see you back tomorrow. We're going to be working on bridges as well as skyscrapers. So keep working on your skyscrapers, but tomorrow we're going to add the element of bridges in as well. All right, take care, everyone. I will see you soon.